This one has a stopwatch running. We're building a system that has to score every single event and return a decision before an action commits. And it has to do it fast. Think fraud scoring, abuse detection, real-time recommendations, dynamic pricing, live alerting. They all share this exact shape. The requirement? Score each event, typically in under 100 milliseconds, at high volume, with no slow database calls in the hot path. Let's design it. Here's the flow. Events arrive on a topic, keyed by the entity, a user ID, a card ID, a device ID. A scoring service consumes them, built on a stream processor like Kafka Streams or Flink, running as several parallel instances. For each event, it does a few things. It joins against a table of entity profiles held in local state. It joins against reference data, also local. It reads a windowed aggregation, like the count of events for this entity in the last 5 minutes, from local state. It runs a rule engine for things like velocity and anomaly checks. And it runs a machine learning model that turns a feature vector into a risk score. Then it emits a decision to a decisions topic. Low score, allow, proceed. Medium score, send to a review queue. High score, block. Now, the whole trick to hitting that latency budget is one idea. Everything is local. There are no synchronous network calls in the hot path. Let me show you the budget, because it's genuinely satisfying. Producing and polling from Kafka, about 10 milliseconds. The local table lookups, about 1 millisecond, because they're co-partitioned in a local state store, not a database call. Reading the windowed state, about 1 more millisecond, also local. The machine learning model inference, about 15 milliseconds. And producing the decision, about 5. Added up, roughly 32 milliseconds, comfortably inside 100. Why is it that fast? Because the profiles and reference data are joined from local state stores, kept current by consuming their own compacted topics in the background. So when an event comes in, there's no round trip to a database for each lookup. The data is already sitting right next to the processor. That's the difference between a system that hits its latency target and one that melts down under load. Let's look at those windowed velocity checks, since they're the heart of the rules. You group the events by entity, apply a tumbling 5-minute window, count them, and filter for, say, more than 10 events in that window. A spike that looks suspicious. You'd use tumbling windows for fixed buckets, hopping windows for a smooth rolling count, or session windows for bursts of activity. And you add a grace period. Accept events that arrive up to 30 seconds late, then close the window. That's you trading a little latency for a lot of accuracy on out-of-order data. Now here's the part that shows real maturity. How you deploy a new model safely. You do not just swap it in and pray. Step 1. Run the new model in shadow mode. It consumes the same events in a separate consumer group and writes its scores to a side topic, taking no action. Step 2. Compare shadow decisions against the live ones and validate the false positive and false negative rates. Step 3. Backtest by replaying the last 30 days of history from the log through the new model. You don't have to wait weeks for fresh traffic to build confidence, because the log already has the history. And step 4. Cut over by swapping the active consumer group. Zero downtime, and the old model stays warm as an instant rollback. That replay capability, that's the log model paying off. And finally, monitoring, with one alert that matters more than all the others. Watch consumer lag on the events topic, and if it climbs above some threshold, alert loudly. Because remember our silent incident story from way back in episode 4? If this scorer falls behind, events are being acted on before they're scored. The fraud check runs after the money's gone, and it throws 0 errors while doing it. Green dashboards, broken system. Also watch your 99th percentile scoring latency, your dead letter queue depth for unscorable events, and your rebalance frequency. since instability there causes lag spikes. So that's a real-time scoring pipeline. Local state for speed, windowing for velocity rules, shadow mode plus replay for safe model rollouts, and a lag alert as your smoke detector. One more build to go. Next episode, we construct an event-sourced service, a system whose source of truth is the log itself. See you there.